S01E03 Vector Space Part 2 Math and Relationships. The most famous equation in the history of artificial intelligence. King minus man plus woman equals queen. Every textbook has stated this since 2013. The problem is, it's not true. Research by Nissim and her team from 2019 reveals what actually happens during this operation. The result most often points back to king himself, not to queen. The king vector is so strong that subtracting man doesn't shift it far enough through the space. And yet, every reg system, every semantic search, every embedding comparison in production relies on these same geometric principles. If you build systems based on vectors, you need to understand where this math works and where it breaks. In this episode, you'll see why this equation fails, how similarity metrics actually work, and what mathematical trick makes three different metrics produce identical rankings. You'll also learn why the geometry of embeddings encodes human biases and what to do about it. In the previous episode, we built intuition, words as points in a multidimensional library. Now we move from the level of metaphor to the level of engineering. Geometry isn't decoration, it's the operating system. The physics of words, where vectors come from. To understand why the Royal equation fails, we first need to understand where these vectors come from, because the way they're created determines their limitations. In the classical approach, known as one-hot encoding, every word was an isolated island. The vector for the word cat was orthogonal to the vector for dog. Mathematically, they had nothing in common. Zero information about similarity. A vector, the length of the entire vocabulary, often 50 to 100,000 positions, with a 1 at a single position and zeros everywhere else. Enormous, sparse, and useless for comparing meanings. Modern embeddings are dense vectors. Each of the 768 positions in BERT, or the 1536 in text embedding ADA, carries partial information about meaning. Semantic similarity is reflected by geometric proximity. Words with related topics sit next to each other in multidimensional space. Words distant in meaning are far apart. Models like Word2Vec, created by Mikolov and his team in 2013, learned these representations by analyzing word co-occurrence. The skipgram variant receives a central word, for example fox, and tries to predict context words such as quick, brown, jumps. SIBO walks in reverse, predicting the central word from the context. In both cases, the principle is the same. A word's meaning is defined by its neighborhood. Words that appear in similar contexts land close together in space. Levy and Goldberg in 2014 demonstrated something fascinating. Word2Vec implicitly factorizes the PMI matrix, the pointwise mutual information matrix. It measures the strength of association between words. Allen and Hospedales in 2019 proved on this basis why vector analogies work. Vector arithmetic doesn't stem from understanding. It stems from co-occurrence statistics. Meaning is statistics, not understanding. Now that we know where vectors come from, it's time for the most spectacular property of this space: arithmetic. The Royal equation, vector arithmetic. The most spectacular property of a well-trained vector space is linear compositionality. Semantic relationships between words are encoded as constant offset vectors. Here's what this means in practice. The classic example from Mikolov's paper. The king vector minus the man vector plus the woman vector should land near the queen vector. The geometry is elegant. By subtracting man from king, we remove the semantic component associated with masculinity. By adding woman, we add the feminine component. The resulting point should lie closest to queen. The arrow from man to king has the same direction and length as the arrow from woman to queen. They form a perfect semantic parallelogram. This is the key point. The relationship is encoded as a constant offset vector. Regardless of where we are in the space, the same offset encodes the same relationship. This property applies to many relationships. Madrid minus Spain plus France gives Paris. The offset encodes the capital country relationship. Actor minus man plus woman gives aktorka. In Polish, actor minus man plus woman gives actress. The offset encodes the morphological gender relationship. Dog minus cat plus kitten gives puppy. The offset encodes the adult-young relationship. Everywhere the same mechanism, a constant offset vector. This sounds too good to be true, because it is. Time for a bucket of cold water. A bucket of cold water, when magic fails. AI engineers need to know about the marketing oversimplification surrounding the royal equation. Nissim and her team in 2019 showed what actually happens under the hood. The result of the king minus man plus woman operation rarely lands precisely at the queen point. Most often, the nearest vector is king himself. The king vector is so strongly correlated with the concept of authority and personhood that the addition and subtraction of gender vectors doesn't shift it far enough to jump to another cluster in the space. This is why standard implementations, for example in the Gensim library, use a procedure that explicitly excludes input vectors from the search results. The algorithm looks for the nearest vector to the operation result that is not king, man, or woman. Only after applying this filter does queen appear at the top of the list. Without this filter, the accuracy of many analogies drops drastically. The situation looks even worse in newer embedding models. In one test with the Granite Embedding 30M English model, queen landed at a position far beyond the top 10, not at second place as textbooks suggest. The structure of vector space is significantly more complex than simple linear relationships. Linearity is a useful approximation for simple relationships. Country capitals, verb forms, simple morphological relations, these work. More abstract relationships, this is where linearity fails. Here's what this means in practice. Don't build production analogy systems on the assumption of perfect linearity. Test results on your own data. Don't trust textbook examples. To even talk about vector proximity, we need a metric. And here begins the debate. Compass or ruler? Compass versus ruler. Similarity metrics. Measuring proximity in multidimensional space requires precise tools because intuition fails. The two main measures are Euclidean distance, the ruler, and cosine similarity, the compass. Cosine similarity is the standard in NLP. It measures the cosine of the angle between two vectors. We compute the dot product of vectors A and B, then divide by the product of their lengths, their norms. The range goes from -1, opposite vectors, to 1, identical vectors. The key property. It ignores vector length, focusing exclusively on direction. And direction represents topic. Length represents the amount of text. Imagine two documents about astronomy, a short abstract and a lengthy monograph. Both cover the same stars, the same galaxies. The monograph vector has a greater magnitude because astronomical terms appear more frequently, yet it points in the same direction as the abstract. Cosine similarity rates them as very similar, close to 1. This is the desired behavior. Euclidean distance measures physical distance in a straight line, the square root of the sum of square differences between corresponding coordinates. In NLP, it's problematic because it's sensitive to text length. Those same two documents about astronomy, identical topic but different length, will appear distant under the Euclidean metric, even though they semantically cover the same ground. The compass measures direction, what the document is about. The ruler measures length, how much of the document there is. For understanding meaning, you want the compass. There is, however, a mathematical trick that makes this debate irrelevant. And this is precisely why the documentation of every vector database uses these terms interchangeably. The normalization trick, hypersphere. In modern vector databases such as Pinecone, Milvus, or FAIS, vectors are normalized using the L2 method before indexing. Each vector is divided by its length, bringing its magnitude to a value of 1. Geometrically, all points land on the surface of a multidimensional sphere, the unit hypersphere. On the unit hypersphere, a fundamental equivalence holds. From the law of cosines, the squared distance between two vectors A and B equals the sum of the squares of their lengths minus twice the product of the lengths times the cosine of the angle. For normalized vectors with a length of 1, the formula simplifies to 2 times 1 minus the cosine of the angle between them. Here's what this means. The smaller the Euclidean distance, the larger the cosine. The larger the cosine, the greater the similarity. Ranking results by Euclidean distance is identical to ranking by cosine similarity. These two metrics, which seemed competitive, on the hypersphere produce exactly the same results. Furthermore, for normalized vectors, the dot product equals the cosine. Since the norms of both vectors equal 1, the cosine formula reduces to the dot product alone. And the dot product is the cheapest to compute. 1 multiplication and summation, no division, no square roots. This is why the documentation of many vector databases uses the terms dot product, L2 distance, and cosine similarity interchangeably, under the assumption that input vectors are normalized. Understanding this subtlety prevents errors when a database returns results in the Euclidean metric, but you expect values on a 0 to 1 scale. A practical rule. Before choosing a metric in a vector database, check whether your embedding model returns normalized vectors. If so, use dot product. It's the fastest option, and the ranking will be identical to cosine similarity. The geometry of embeddings encodes more than word meanings. It also encodes the biases of the people who wrote the training data. Bias encoded in geometry. Vector space is not neutral. Models learn from internet data and inherit human stereotypes. Bias isn't a bug in the algorithm. It's a faithful geometric reflection of the prejudices contained in the training corpus. Research by Bolugbashi and his team from 2016 revealed disturbing relationships. The programmer vector minus man plus woman points toward the homemaker vector. The doctor vector minus father plus mother lands near the nurse vector. The same semantic parallelograms that encode capital country relationships also encode gender stereotypes. Here's what this means in practice. If you use such embeddings to sort resumes, the system may discriminate against women applying for technical positions. Not because someone programmed discrimination, only because in the training corpus, the word programmer was geometrically closer to masculine words. The algorithm faithfully reproduced the biases contained in the data. Debiasing techniques exist. Bolugbashi and his team proposed projecting vectors onto a gender-neutral subspace. The WET metric, the Word Embedding Association test, allows measuring bias strength by computing cosine similarity between word groups, for example, professions versus gender. Bias auditing in embeddings should be a standard step before deploying any system that ranks people. This isn't an ethical detail. It's engineering responsibility. Everything we discussed applies to static embeddings. Modern models solve their biggest weakness. From static to context. Bridge to self-attention. Everything we discussed, arithmetic, metrics, bias, applies to so-called static embeddings, word2vec, glove. They have one fundamental weakness: ambiguity. In word2vec, the word bank has one vector. Regardless of whether we're talking about a river bank, a financial bank, or a bank shot in billiards, the model uses the same representation, an average of all meanings. It's like a map, where Warsaw and Washington are drawn at the same point because both are capitals. The information exists, but is blurred to uselessness. The breakthrough came with the introduction of contextual models. Elmo in 2018, and Bert in 2018. In these models, a word's vector isn't retrieved from a static table. It's generated dynamically by a neural network based on the entire sentence. Every occurrence of a word gets its own unique vector. The word bank in the sentence, "The fisherman sat on the riverbank," its vector sits close to the words shore and water. The same word bank in the sentence, "She deposited money at the bank," its vector sits close to the words finance and account. Two completely different vectors for the same word. Context determines the representation. It's the self-attention mechanism that allows the model to color a word's vector with the meanings of its neighbors. And this mechanism uses the dot product, the same one we learned about in this episode, to calculate how much each word should influence the representation of every other word in the sentence. If you want to know how the self-attention mechanism uses these same dot products to build context, how query, key, and value matrices create dynamic representations, click the next episode. If this video helped you understand something new, subscribing and commenting helps me create more content like this. Geometry is the API.